Hi, my name is Nastaran Hajinazar, and I'm going to present SIMDRAM, a framework for bit serial SIMD processing using DRAM. To begin, I will give a high-level summary of the talk. Our primary motivation in this work is the increased interest in processing using memory architectures, which can efficiently perform bulk bitwise computations. However, current processing using memory architectures are not yet widely applicable, as they only support a limited and rigid set of operations, lack the flexibility to support new operations, and often require significant changes to the DRAM architecture. Accordingly, our goal in this work is to design a processing using DRAM framework that can efficiently implement complex in DRAM operations, provide the flexibility to support new desired operations, and require minimal modifications to the DRAM architecture. To this end, we introduced SIMDRAM, an end-to-end processing using DRAM framework that provides the programming interface, the ISA, and the hardware support for efficiently computing complex operations while providing the user with the ability to implement arbitrary operations as required. SIMDRAM uses a massively parallel in-DRAM SIMD substrate that requires minimal changes to the DRAM architecture. Our evaluations show that SIMDRAM provides 88 times and 5.8 times the throughput and 257 times and 31 times the energy efficiency of a baseline CPU and a high-end GPU respectively for 16 in-DRAM operations. SIMDRAM also provides 21 times and 2.1 times the performance of a baseline CPU and a high-end GPU respectively for 7 real-world applications. Here's the outline of my talk today, and I will start by briefly discussing processing using DRAM. The growing size of data in modern applications has led to high energy and latency costs for computation in traditional computer architectures. Prior work showed that the cost of data movement between the main memory and the CPU across the bandwidth-limited and power-hungry memory channels is much higher than that of computation and can consume more than 60% of the total system energy in modern systems. To mitigate such costs, the processing in memory or PIM paradigm moves computation closer to where the data resides, reducing and in some cases eliminating the need to move data between memory and the processor. Processing using memory is one of the promising approaches to PIM, which exploits the analog operation principles of the memory circuitry to perform computation, and benefits from the large internal bandwidth and parallelism available inside the memory arrays. A common approach for processing using memory architectures is to make use of bulk bitwise computation, as many widely used data-intensive applications, such as databases, neural networks, and graph analytics, heavily rely on a broad set of simple logical operations and more complex operations. I will now give a brief background on how DRAM operates and how its operating principles can be used to build processing using DRAM architectures. A DRAM module is composed of many DRAM chips. Each DRAM chip contains several banks, and each bank has many subarrays, which are in fact two-dimensional arrays of DRAM cells. The DRAM cells in the subarray are horizontally connected using a word line and vertically connected using a bit line. The bit lines are connected to an array of sense amplifiers called row buffer. A DRAM cell is composed of a storage capacitor, which holds the value stored in the DRAM cell, and an access transistor, which enables and disables the charge flow from the storage capacitor to the bit line. DRAM cell operates using three main commands: activate, read or write, and precharge. To read the charge level stored in the storage capacitor, the memory controller issues an activate command. Once the DRAM array receives the activate command, the word line of the target row is raised, which connects all the cells along the row to their respective bit lines. As a result, the storage capacitor shares charge with its corresponding bit line and results in a positive deviation of the bit line. Next, the sense amplifier is enabled and the positive deviation in the bit line is sensed and amplified. Once the amplification is finished, the charge in the storage capacitor is fully restored and the row buffer contains the value stored in the cell. The memory controller then issues read or write commands to the columns within the activated row. To prepare the DRAM array for future accesses, the memory controller issues a precharge command. To this end, first, the capacitor is disconnected from the bit line by disabling the word line. As a result, the bit line voltage is restored to its initial state. And finally, the sense amplifier is disabled. Now DRAM array is ready to perform the next accesses. Now let's see how we can use the internal DRAM cell operation to perform in-DRAM computation. We start with performing in-DRAM row copy. Let's assume we want to copy the value stored in source row A to the destination row B. The two rows share the same bit line. RowClone enables copying the source row A to the destination row B in the same subarray by issuing two consecutive activate commands to these two rows, followed by a PRECHARGE command. First, an activate command is issued to source row A, which pulls the bit line to the value of the cells connected to them and copies the content of the source row A into the row buffer. The second activate command to the destination row B connects the cells in row B to their bit lines. Now, because the sense amplifiers have already sensed and amplified the value stored in the source row A by the time that row B is activated, the data in each cell of row B is overwritten by the data stored in the row buffer, copying the data in the source row A to the destination row B. Finally, the PRECHARGE command prepares the DRAM array for the next accesses. We can follow a similar principle to execute majority functions in DRAM. To refresh your memory, the output of a majority function is 1 only if more than half of its inputs are 1. Let's assume we want to compute the majority of the values stored in the three rows A, B, and C. Ambit, a prior processing using DRAM architecture, shows that simultaneously activating three DRAM rows using a DRAM operation called triple row activation can be used to perform bitwise majority operations on the values stored in the cells of the three rows. Let's see how it works. First, activating all three DRAM rows simultaneously results in a positive deviation of the bit line. After sense amplification, the sense amplifier drives the bit line to VDD, which is the majority of the values stored in the three cells in this example. The cells are then fully charged because of the amplified voltage of the bit line. In other words, all three DRAM cells are overwritten by the results of the majority operation. At the end of the operation, a PRECHARGE command is issued to prepare the DRAM array for future accesses. Ambit uses triple row activation command sequence to implement Boolean and or operations by simply setting one of the inputs, for example, input C, to 1 or 0. The AND operation is performed by setting C to 0, and the OR operation is performed by setting C to 1. In order to perform processing using DRAM, Ambit splits the DRAM rows in the subarray into three groups. Compute rows, which can execute triple row activation, two control rows that are pre-initialized with all ones and all zeros, and are used to control performing AND or OR operations during a triple row activation, and regular data rows, which are the remaining rows in the subarray and are used to store users' data as usual. Ambit requires only minimal modifications to the DRAM subarray. More specifically, while a regular row decoder is used to activate rows in the data and control groups, Ambit uses a special row decoder for the compute rows to perform triple row activation. To compute row decoder, the compute row decoder can simultaneously activate three rows using a single address, which is used to perform majority function on the values of the three activated rows. These modifications impose less than 1% area overhead in a commodity DRAM chip. Inspired by RowClone and Ambit, many prior work have explored DRAM designs as well as other memory technologies that are capable of performing computation using memory. However, they suffer from three major shortcomings. First, they support only basic operations and fall short on efficiently supporting more complex operations, which limits their applicability. Second, they support only a limited and specific set of operations, lacking the flexibility to support new operations and cater to the wide variety of applications that could potentially benefit from processing using DRAM, or often require significant changes to the DRAM subarray, which makes them costly. This highlights the need for a framework that aids the general adoption of processing using DRAM by efficiently implementing complex operations while providing the flexibility to support new desired operations. Accordingly, our role in this work is to design a processing using memory framework that efficiently implements complex operations, provides the flexibility to support new desired operations, and minimally changes the DRAM architecture. I will now describe our proposed processing using DRAM framework called SIMDRAM. SIMDRAM is an end-to-end processing using DRAM framework that provides the programming interface, the ISA, and the hardware support for efficiently computing complex operations in DRAM and providing the ability to implement arbitrary operations as required. SIMDRAM achieves this using an In-DRAM massively parallel SIMD substrate that requires minimal changes to the DRAM architecture. I will now describe the DRAM substrate that SIMDRAM uses for in-DRAM computation. We built the SIMDRAM framework around the DRAM substrate that enables two key techniques. First, vertical data layout in DRAM. Prior works showed that employing a vertical layout for the data in DRAM eliminates the need for adding extra logic in DRAM to implement bit shift operation, which is essential for many complex operations. Employing vertical data layout provides SIMDRAM with two key benefits: implicit shift operation and massive parallelism, where each DRAM column operates as a SIMD lane. The second key technique used in SIMDRAM substrate is majority-based computation. As opposed to using basic logic operations such as AND or NOT to implement in-DRAM computation, SIMDRAM uses logically complete set of majority and NOT operations to implement in-DRAM computation. Doing so enables SIMDRAM to achieve higher performance, higher throughput, and lower energy consumption compared to using basic logical operations for in-DRAM computation. Now let's take a look at the SIMDRAM framework. The SIMDRAM framework is composed of three key steps. The first step of the framework builds an efficient majority NOT representation of a given desired operation from its AND or NOT-based implementation. The second step allocates DRAM rows to the operations input and outputs to generate the required sequence of DRAM commands to execute the desired operation, which is called a microprogram. The third step executes the microprogram to perform the operation. SIMDRAM uses a control unit in the memory controller that transparently issues the sequence of commands to DRAM as dictated by the microprogram. Now let's take a more detailed look into the first step of the SIMDRAM framework. As Ambit showed, it is quite trivial to convert a Boolean equation to its equivalent majority equation, as each two-input AND operation can be implemented using a three-input majority operation, where one of the inputs is tied to logic 1, and an OR operation is implemented using a three-input majority operation, where one of the inputs is tied to logic 1. Accordingly, the first part of the transformation process in step 1 of the SIMDRAM framework simply replaces the AND and OR primitives with majority primitives in the logic representation of the desired operation. However, naively converting AND and OR primitives with majority results in an implementation of the operation that correctly replicates the functionality of the initial AND or NOT-based implementation, but it's often inefficient. To address this issue, the second part of the transformation process takes the inefficient majority NOT-based implementation and uses a greedy optimization algorithm that applies a series of transformation rules to reduce the number of majority operations required to perform a desired operation. For example, this picture shows the generated majority NOT-based implementation to compute the carry propagation logic in a full addition, which requires only one majority operation instead of 4. Therefore, step 1 generates an optimized majority NOT implementation of the desired operation. Let's now take a look at the step 2 of the SIMDRAM framework. Each SIMDRAM operation is stored in the memory as a microprogram, which actually is a series of DRAM commands such as activation and precharge that SIMDRAM uses to execute the operations in DRAM. Accordingly, the goal of the second step of SIMDRAM framework is to take the optimized majority NOT-based implementation created in step 1 and generate a microprogram that executes the desired SIMDRAM operation in DRAM. To this end, the second step performs two key tasks on the optimized majority-based implementation of the operation. First, it allocates DRAM rows to the operations operands, and second, it generates the microprogram that performs the series of DRAM commands on the rows containing the operands that is required to perform the desired in-DRAM operation. Now let's take a look at the first task of step 2. The goal of task 1 is to allocate DRAM rows to the input operands of each majority primitive in the majority not-based implementation of the operation. When allocating DRAM rows to the operands, SIMDRAM takes into account two extra constraints that are specific to processing using DRAM. First, the number of compute rows reserved to perform bitwise operations is limited. And second, performing majority operation in DRAM has destructive behavior. In other words, as we saw earlier, the triple row activation operation overwrites the original values of the three input rows with the output of the majority operation. Based on these two constraints, we present a new allocation algorithm inspired by the linear scan register allocation algorithm. Our allocation algorithm takes as input the majority not implementation of the operation generated in step 1 and starts by assigning the inputs of the majority of each majority logic primitive to the available compute rows one at a time. Since the number of compute rows are limited, this step of the algorithm assigns only as many inputs to the compute rows as the number of compute rows that are not allocated to any operand yet. Next, performing triple row activation in the compute rows in this example computes the majority of A and B and carry in, which is in fact computing the carry out value. As a result of the destructive behavior of the triple row activation in DRAM, the carry out is stored in all three input rows at the end of the triple row activation process. Our allocation algorithm takes advantage of this behavior and reuses these rows as inputs of the next majority operation in case the value stored in any of these rows is an input for the next majority operation. Now let's take a look at the second task of this step 2, which generates the microprogram to perform the desired DRAM computation. Task 2 works in three key parts. The first part generates an initial microprogram. This part first copies the three operands from the data rows to the compute rows allocated to them in task 1, using row copy operation, which as we saw earlier contains two activations followed by a precharge. Once all inputs of the majority operation are copied to the allocated rows, a triple row activation is issued to execute the majority operation. Finally, another row copy is issued to copy the output of the majority operation that is stored in the compute rows back to the destination data rows if needed. The resulting sequence of DRAM commands represents the initial microprogram. The second part of task 2 optimizes the initial microprogram by leveraging the structure of our processing using PuM Substrate, including the ability to coalesce multiple row copy operations into a single one, and merging a majority and a row copy operation in a single operation. With these two optimizations, an optimized microprogram is generated that requires fewer DRAM commands to perform the same desired in-DRAM operation. I invite you to read our paper for more details about the two optimizations mentioned here. Once all potential operations are coalesced, the framework now has an optimized microprogram that computes the desired operation for operands of size 1 bit. The final part of task 2 generalizes this 1-bit version of the operation into an n-bit version by repeating the DRAM commands in the optimized microprogram for n times. The final output is an optimized microprogram that requires minimal number of DRAM commands to perform the desired in-DRAM operation on operands of size n. The final microprogram is then stored in a reserved region of DRAM for future use. Also, a new SIMDRAM instruction called BBUP is created specifically for this new in-DRAM operation and added to the CPU ISA. The BBUP instruction is used later by the programmer to perform the added SIMDRAM operation. Now let's take a look at step 3, the final step of SIMDRAM framework. SIMDRAM uses a control unit in the memory controller that handles the execution of the microprogram at runtime transparently to the programmer. To perform a SIMDRAM operation, program uses the appropriate BBUP instruction that refers to the target operation. Upon receiving the BBUP instruction, the control unit loads the microprogram corresponding to the BBUP from the main memory and performs the requested SIMDRAM operation by issuing a sequence of DRAM commands stored in the microprogram of that operation. At the end of the microprogram's execution, the outcome of the SIMDRAM operation is stored in memory. I invite you to read our paper for a detailed reference implementation and the microarchitecture of the SIMDRAM control unit. Next, I will discuss the integration of the SIMDRAM framework in the system. We employ several techniques to efficiently integrate SIMDRAM in the system. The first technique is regarding efficient transposing of the data layout in DRAM that enables SIMDRAM to store the data required for in-DRAM computation in the vertical layout. While SIMDRAM operates on vertically laid out data, the other system components, including the CPU, expects the data to be laid out in the traditional horizontal format, making it challenging to share data between SIMDRAM and the CPU. To address this issue, SIMDRAM uses a specialized hardware unit placed between the last level cache and the memory controller called the Data Transposition Unit to transform the data layout from horizontal to vertical and vice versa. The transposition unit tracks SIMDRAM objects or data objects used in SIMDRAM operation and ensures that their data is stored in the vertical layout and ready for SIMDRAM computation whenever the data is present in DRAM, and in the horizontal layout whenever the data is present in the cache so that it is ready for computation in the processor. Our evaluations show that the transposition unit imposes very low overhead on the throughput of SIMDRAM operations, while imposing very low area overhead in commodity DRAM chips. I invite you to read our paper for more details about the transposition unit and the rest of the SIMDRAM system integration techniques that we introduced, such as the programming interface of SIMDRAM, how SIMDRAM handles page faults, address translation, coherence, and interrupts, how SIMDRAM manages computation on large amounts of data, security implications of SIMDRAM, and the current limitations of the SIMDRAM framework. I will now present the results. We implement SIMDRAM using Gem5 simulator. We compare SIMDRAM against three baselines: a multi-core CPU, a high-end GPU, an Ambit, and a state-of-the-art in-DRAM computing mechanism. We evaluate three different configurations of SIMDRAM. One bank configuration, where a single DRAM bank out of the 16 banks is extended to enable SIMDRAM computation. This enables SIMDRAM to execute operations over 64,000 SIMD lanes. We also evaluate SIMDRAM with 4 SIMDRAM-enabled banks and 16 SIMDRAM-enabled banks. To demonstrate its generality, we evaluate SIMDRAM using 16 complex in-DRAM operations and 7 commonly used real-world applications from various domains. First, we compare the throughput across all 16 SIMDRAM operations. Here, the x-axis shows each one of the three baselines that we evaluate, and the y-axis shows the average throughput in giga operations per second normalized to the corresponding baseline. We make 3 observations. First, SIMDRAM with a single bank provides 5.5 times the throughput of the baseline CPU. This value increases to 22 times the throughput of the baseline CPU using 4 DRAM banks, and to 88 times using 16 DRAM banks for in-DRAM computation. Second, SIMDRAM with a single bank is not enough to outperform the throughput of the GPU. However, with 4 DRAM banks, SIMDRAM provides 1.5 times the throughput of the GPU, which scales to 5.8 times when using 16 DRAM banks. Third, compared to Ambit, SIMDRAM with a single bank provides 2 times the throughput of Ambit, while SIMDRAM with 4 banks provides 7.9 times, and SIMDRAM with 16 banks provides 31.6 times the throughput of Ambit. We conclude that SIMDRAM can largely outperform all 3 state-of-the-art baselines for a wide range of operations. We also evaluate the energy efficiency of SIMDRAM across all 16 operations. Here, the x-axis shows each one of the 3 baselines, and the y-axis shows the average energy efficiency in throughput per watt normalized to the corresponding baseline. We make the following observations. SIMDRAM provides 257 times the energy efficiency of the CPU baseline, 31 times the energy efficiency of the high-end GPU, and 2.6 times the energy efficiency of Ambit. We conclude that SIMDRAM is more energy efficient than all state-of-the-art baselines. Finally, we compare the speedup that SIMDRAM provides across all 7 commonly used real-world applications. Here, the x-axis shows each one of the three baselines that we evaluate, and the y-axis shows the average throughput normalized to the corresponding baseline. We make these observations. First, SIMDRAM with a single bank provides 3 times the speed of the baseline CPU, which scales to 8.7 times using 4 DRAM banks and 21 times using all 16 banks for in-DRAM computation. Second, SIMDRAM with a single bank and with 4 banks is not enough to outperform the GPU. However, by using all 16 SIMDRAM-enabled banks, SIMDRAM provides 2.1 times the speedup of GPU on average across all 7 applications. And finally, SIMDRAM with a single bank provides 2.5 times the speedup compared to Ambit, which scales to 7.3 times using 4 DRAM banks and 17.5 times using all 16 SIMDRAM banks for in-DRAM computation. We conclude that SIMDRAM can effectively and efficiently accelerate many commonly used real-world applications. I invite you to read our paper for more details and evaluations, such as the reliability of SIMDRAM operations, the overhead of transposing data layout, the area overhead of the SIMDRAM framework, SIMDRAM's performance and energy benefits over a closely related processing using cache architecture, and more. Now let me conclude the talk by giving the summary. We introduced SIMDRAM, an end-to-end processing using DRAM framework that provides the programming interface, the ISA, and the hardware support for efficiently computing complex operations while providing the user with the ability to implement arbitrary operations as required. This is done using a massively in-DRAM SIMD substrate. Our evaluations show that SIMDRAM provides 88 times and 5.8 times the throughput and 257 times and 31 times the energy efficiency of a baseline CPU and a high-end GPU, respectively, for 16 in-DRAM operations, and 21 times and 2.1 times the performance of a baseline CPU and a high-end GPU, respectively, for 7 real-world applications. We conclude that SIMDRAM is a promising processing using memory framework that can ease the adoption of processing using DRAM architectures and improve the performance and efficiency of processing using DRAM architectures. Thanks for listening to my talk, and for more details, I invite you to read our ASPLOS 2021 paper.